Hello everybody and welcome back. This is going to be section 2.2. Today we're talking about organizing quantitative data, just a few of the most common displays. Today we're going to organize discrete data and continuous data into tables, and we're going to construct histograms of both discrete and continuous data. And I'll show you how to make a stem and leaf plot, how to make a dot plot, and we will talk a little bit about the shape of a distribution. Here we go. Now, first of all, remember that discrete data is counted and continuous data is measured. And usually discrete data will be whole numbers. Continuous data will usually have decimal places, although it doesn't have to, but it usually will. Now, when we make a frequency distribution for quantitative data, it's very much similar to the process we had for qualitative data, but instead of having categories, we will divide the data into classes. If a data set contains only a few discrete values that are close together, we can choose for each class to contain only one value. And that's what we'll look at in this first example. Okay, here we have the manager of a Wendy's wants to know the typical number of customers who arrive during the lunch hour. The data represent the number of customers who arrive at Wendy's for 40 randomly selected 15-minute intervals of time during lunch. Construct a frequency and a relative frequency distribution. Okay, so here we have our table of raw data, and we're going to make classes that each only contain one value. So let's find the smallest value in this table, which I guess is 1, and the largest value, which is 11. And we will need to list each of those in this first column. Okay, now let's tally the data. And again, I like to go whichever way is going to get me the shortest line of numbers. So I'll go down this table. First we have 7, then 5, then 2, then 6, then 2, and then we have 6, 6, 7, 5, 2. And then we have 6, 6, 1, 5, 9. And then we have 6, 11, 2, 3, 7. And then we have 4, 4, 4, 7, 5. And then we have these last three columns. I'll let you go ahead and fill those in. Okay, now let's tally up our frequencies. So for the first one we have 1. And then for the value 2, we have 6 occurrences, and then we have 1, and you can tally up all the way down. You should end up with 11 occurrences of the 6 and 0 occurrences of 10. And now let's calculate relative frequency for each of these. There are 40 numbers here, so we'll take each value and divide by 40. 1 divided by 40 will be 0.025. 6 divided by 40 is 0.15, and then I'll let you fill in the rest. Okay, now let's talk about classes that are not just single values. So classes are categories into which quantitative data are grouped. In the last example, again, each class only contained a single value. But when a data set consists of a large number of different discrete data values, or when a data set consists of continuous data, we must create classes using intervals of numbers. So here you see a frequency distribution where the classes are not just a single value. So when you have classes like this that include a range of numbers, the left number is called the lower class limit. So the lower class limits are the smallest number in each class, and the upper class limits are the largest number in each class. So our upper class limits are 34, 44, 54, and so on. And the class width is not what you think. You might think that class width would be the difference between the upper and the lower. It's not. The class width is the difference from lower class limit to the next lower class limit. So for this example, the class width is 10. Now this is very important. Class limits must be defined so that each data value fits into only one class, and also so that every possible data value fits into some class. So notice this frequency distribution, which is made from discrete data. So the first class starts at 25 and goes to 34, and then the next class starts at 35 and goes to 44. So because we're dealing with discrete data, we can see that where the first class ends, the second class picks up. And there's no danger of us having a data value that's 34.5 or something like that, because this is discrete data. So you can look at the upper class limit and the next lower class limit and see that they are consecutive, so every number will fit into one class or the other. And you can also see that they don't overlap, so no data value is going to fit into two classes. Now let's do an example with discrete data where we will have to form classes that cover a whole interval of numbers. Okay, this one says, the following data represent the time between eruptions in seconds for a random sample of 45 eruptions at the Old Faithful Geyser in Wyoming. Construct a frequency and relative frequency distribution of the data. Use a lower class limit of 670 for the first class and a class width of 10. Okay, well, we know that the first class has to start at 670, but I think it will be helpful for us to try to find the largest data value in this table. So I'm looking down this first column and I see a 730, and I don't see anything here that beats that. And here is a 738, so that may be the largest, and I believe it is. So when we form our classes, we'll start at 670, but we'll need to go high enough to include these larger data values. So here we go. Starting at 670 and using a class width of 10, we'll say 670 plus 10 is 680, then 690, and continue down. Remember, we have to have a class large enough to accommodate this largest data value. So now the next class would need to start with 740, and I don't have any values that large, so this is the last class we will need. And since our data is discrete, if this class starts at 680, I know that the first class must end at 679. So now I can just take the 679 and add 10 all the way down to form all the upper class limits. Okay, now let's tally the data, and I'll do the first few rows with you and then you can do the rest. So here I have 728. 728 is going to fit into this next to last class. Then I have 678, that's going to fit into this first class. Then 723 fits here. 735 fits here, and 703 fits here. Okay, now we have 730, 722, 708, 714, 713, and I'll do one more row with you. 726, 716, 736, 719, and 672. Okay, now I'm going to let you do the rest of them. Okay, now let's go ahead and sum up each of the tallies. So this first class here has a count of 2. The second class is empty, so I can't leave it out now. It's important that we include all the classes from first to last. Even though this class is empty, I cannot leave it out, so I'll put a frequency of 0. And the third class has a frequency of 7, then 9, 9, 11, and 7. And now let's get our relative frequency. This table contains 45 numbers, so we'll just divide each of these numbers by 45. 2 divided by 45 is 0.044, and so on. Now you may have noticed that the choices for the lower class limit of the first class and the class width were rather arbitrary in our last example. There's no right number of classes. If somebody else had chosen a different starting place or a different class width, that wouldn't be wrong. It's pretty much just a matter of judgment. We typically try to have between 5 and 20 classes, and that varies depending on your data. You just need to try different class widths until you find one that best describes the data. Too many classes won't summarize the data in a useful way, and too few classes will bunch the data up so that it's hard to see a pattern. So it's our job to try to find a class width that lets us look at the frequency table and see how the numbers are arranged. Now you might have noticed that in the last example we did, the choices of the lower class limit of the first class and the class width were rather arbitrary. They were just given to us in the problem and we didn't have to figure them out ourselves. And in fact, those numbers could have been different. 670 didn't have to be the lower class limit of the first class, and 10 didn't have to be the class width, although those were very convenient numbers. So the idea of making a frequency table is all about using convenient values that make it easy for your reader to understand how the data are laid out. There's no right or wrong number of classes, although we do typically try to have 5 to 20 classes. A larger data set will require more classes, and a smaller data set can get away with fewer classes. If you have too many classes for your data set, then the frequency table won't summarize the data in a useful way. If you have too many classes and you only have 1 or 2 or 3 values in each class, then you're not really much better off than you were when you had the table of raw data. On the other hand, too few classes will bunch the data up so that it's hard to see a pattern. So now I'm going to give you some guidelines for choosing the lower class limit of the first class and also the class width. And keep in mind that these are not rules. So you see Captain Barbosa here. You remember the line. They're more what you'd call guidelines than actual rules. So I don't want you to think of this as a formula for getting the lower class limit of the first class or a formula for getting the class width, but it's just a way of thinking through the process. So if you need to choose your own lower class limit of the first class, here's what you should do. Find the smallest observation in the data set and then either use that as the lower class limit of your first class or use a convenient number that's slightly lower than that. Like if you'll remember in the last example we did, I think the smallest data value we had was 672 or something, but they let us use 670 as the lower class limit of the first class because 670 is a nice round number. And for another example, if the smallest value is 3.22, then it would be convenient to choose 3 maybe as the first lower class limit. It entirely depends on your data set. So that's a choice you can make. And then to determine the class width, first decide on the number of classes. The smaller the data set that you have, the fewer classes you'll need. And again, somewhere between 5 and 20 is a good place to start. And then your class width is going to be the largest value in your data set minus the smallest value, and then divide that by the number of classes you want. And whatever you get here, round it up to a convenient number. So let's say that you do this calculation and you come up with a class width of 8.39. Okay, you round that up maybe to 9, then to every lower class limit you're going to have to add 9. And you say, well, that's a little inconvenient. I don't really want to have to add 9. I'd rather add 10. That's fine. Go ahead and round it up to 10. It doesn't have to be the next number. You just round it up to a convenient number. And again, it depends on your data set as to what the convenient number will be. Okay, now where we're headed is we want to be able to construct a histogram. A histogram is constructed by drawing rectangles for each class of data. It's very similar in concept to a bar graph. The height of each rectangle is the frequency or the relative frequency of the class. The width of each rectangle should be the same for each class, and the rectangles must touch. So here is the biggest difference in looks between a bar graph and a histogram is that the rectangles on a bar graph were not allowed to touch, but the rectangles on a histogram must touch each other. But the biggest defining difference between a bar graph and a histogram is that a bar graph has categories along the horizontal axis, whereas the histogram will have numbers on the horizontal axis. And that's the defining difference between a histogram and a bar graph. Now, just like with bar graphs, the vertical axis doesn't need to go much higher than the tallest rectangle. Now let's talk about how the bars are arranged in relation to the numbers on the horizontal axis. For single value grouping, the horizontal axis should be labeled with each value, and the bar should be centered over its corresponding axis label. So you can see here is my class of 0. There are 4 observations of 0. There are 2 observations of 1, and so on. And you can see that the class of 9 is empty. And notice that each rectangle is centered over its tick mark. On the other hand, for data that's organized into classes where the classes are intervals, the horizontal axis should be labeled with the lower class limit of each class, and the bars should be positioned between the tick marks. So let's look at this histogram that represents the IQs of 7th grade students. And you know, IQs are discrete data. Now we see that the lower class limit of the first class is 60, and the lower class limit of the second class is 70. Now the upper class limits are not labeled, but they don't really have to be, because we know that on a frequency distribution, the classes have to be arranged so that there are no gaps between the classes and there are no overlaps between the classes. So where one class ends, the next class begins. And since this data is discrete, we can assume that the upper class limit of the first class is 69. Also notice that the bars are not centered over a tick mark, but between the tick marks, because the tick marks represent the lower class limit of each class. Now let's construct a frequency histogram using the frequency table that we constructed in the first example. You'll remember that here are our single value classes, and here are our frequencies. So first of all, I noticed that the tallest bar is going to need to be 11 units high, so I will just count by 2s, and that will give me 2, 4, 6, 8, 10, 12 here at the top of the vertical axis. And my horizontal axis needs to be labeled with numbers from 1 to 11. And even though the 10 has 0 observations, I still can't leave it out. So here I have labeled my horizontal axis. Now a histogram without labels on both axes is completely useless. You absolutely must label the axes if you're drawing these by hand. And let's go ahead and draw our rectangles. So for the class of 1, we have a frequency of 1, so that bar will come up to here. And for the class of 2, we have a frequency of 6, so that bar will come up to here. And notice that they touch. That is absolutely critical. The bars must touch. And then for the class of 3, we have an observation of 1, then 4, 7, 11, 5, 2, 2, 0, so I left that one blank, and 1. And I would encourage you to pause the video and get yourself a straight edge and draw this histogram on your own, because when you do it yourself instead of just watching somebody else do it, it really does make you think through the process of how the histogram is made, and you'll be so much better off having drawn it yourself. So go ahead and do that, and when you're done, we'll go on and draw the next one, which is going to be relative frequency. So now here is our frequency distribution again, but this time we want to construct a relative frequency histogram, which means that the vertical axis will need to be labeled with numbers that can accommodate these values. So remember that we want the tallest bar to come nearly to the top of our vertical axis. So it looks like the tallest bar is going to need to be 0.275. Now remember that when you label the vertical axis, you want to use numbers that are convenient. So I'm thinking 0.275 is very close to 0.3. So I'm just going to put 3 tick marks here and let these be 0.1, 0.2, 0.3. And I've also gone ahead and put halfway marks in between. So this one will be 0.05, then 0.15, then 0.25. That is certainly not the only way to do that. And the more you've done it, the more experience you have, the easier it will be. But that's just one way that occurred to me because 0.275 is so close to 0.3. And now let's go ahead and label the horizontal axis with each of our values. And remember that because these classes are single value classes, the bars will be centered over the single value. All right, the first bar is going to be 0.025 units tall. Now my first tick mark is 0.05, so that means 0.025 is going to be halfway, so right there. And the second bar is 0.15, which is going to be right here. The third bar is 0.025, which is the same height as the first one. The next bar is 0.1, which is going to be about this tall. And then 0.175, which will be halfway between 0.15 and 0.2, so right here. And then 0.275 will come all the way up here. And 0.125 right here. And then 0.05 again right back down here. We had two bars in a row that were 0.05, and then remember the class of 10 is empty, so leave a space for that, and then 0.025 right here. And so here is our relative frequency histogram. And so notice it is the same shape that we had on the previous histogram. There's the previous histogram, there's the new one, and the only difference is that the vertical axis is labeled with the relative frequencies instead of the frequencies. Now we're going to construct a frequency histogram using the frequency table from the second example we did, which was the Old Faithful Geyser in Wyoming. Remember that big table of data that we looked at? And it was discrete data. And remember they gave us the lower class limit of the first class as 670 and the class width was 10. So 670 plus 10 was 680, plus another 10 was 690, and so on. Okay, so what we will do is we will label the horizontal axis with the lower class limit of each class. Now you'll notice I've put a little break symbol here, and that's just because we don't want to count from 0 to 670, but where the axes cross really is supposed to be 0. So whenever I can remember to, I try to put a little break symbol there. It just alerts the reader that, hey, we're not starting at 0. Sometimes it's not reasonable to start at 0, but you still need to alert the reader that you've messed with the horizontal axis here by not starting at 0. Okay, so 670, 680, and we've labeled all of the lower class limits. Now look how I went ahead and put a tick mark for 740. Even though we don't have a class that starts with 740, remember the bars are going between the tick marks, so I just needed to have a tick mark on the end here to accommodate our last rectangle that's going to go right here. Okay, now let's label the vertical axis, and because these are frequencies, we'll be using this column. So my tallest bar is going to be 11 units tall, so I need the 11 to be up here near the top somewhere. And you could do like I did last time and count by 2s, or I'm going to go ahead and count by 1s. Either way is fine. And now let's draw our rectangles. So for the first class we had a frequency of 2, so that bar is going to be this tall, and remember the bars go between the lower class limits. So right here I'm going to put a bar that's 2 units tall. And then the next bar is actually 0, so we'll have a hole here. And then the next bar, the third one, is 7 units tall. It will go here, and it will be about this tall. And then we have the next class is 9 units tall, so it'll be this tall. And then another 9, then 11, then 7. And so now you see why, even though I don't have a class that starts with 740, it does sort of serve as the end of our last class. Now we'll do the same thing for the relative frequency. So again, go ahead and label your horizontal axis with the lower class limits of every class. And this time we'll need to put labels on the vertical axis that will accommodate our relative frequencies. So I noticed that our largest relative frequency is 0.244, and that's very close to 0.25. So I'm going to go ahead and put marks on here that represent 0.1 and 0.2, and then in between I'll count by fives. So this first mark will be 0.05, then 0.15, and then 0.25 right here. Okay, our first bar is 0.044, and we have a label here that's 0.05, so the first bar needs to come just below that height, and the second one is empty, of course, and then the next one is 0.156. Now, you know, we're estimating. This is a hand-drawn graph. It's not going to be exact to the third decimal place, so you know, I see 0.15 here. I know 0.156 is just slightly taller than that. Maybe not even enough to see on the graph. So I'm going to draw my third rectangle there, and you can see that the height is just a little more than 0.15. And then we have 0.2, and then we have another bar of 0.2, and then we have 0.244, which is going to come up almost to the 0.25 mark. And then we have 0.156, which I believe is the same height as this one. And that's it. So drawing the relative frequency histogram really isn't as daunting as it probably seems at first when you have, you know, numbers that are pretty ugly like these are. I think the key is in labeling your vertical axis with convenient numbers, and then just realizing that it's not going to be exact to the third decimal place. We are still drawing by hand after all, so it's going to be rounded off. But if you would like to compare to the frequency histogram that we had, let's flip back, and there it is, and there's the relative frequency. And you can see that, I mean, apparently I got my bars a little taller on the second one, but the general shape is the same. So the shape does not change. Really all that's changing is the vertical axis.